there are so many areas in Earth, oceanographic, and engineering sciences that deals with processes in three-dimensional space as well as time. And a very powerful mathematical subdiscipline that enables those studies that's called vector calculus. And of course, the basic element of vector calculus is vectors. So that will be the topic of this introductory video. After viewing the video and working through the problem sets, you will be able to describe vectors in Cartesian coordinates specifically. You'll be able to use the dot product or cross product of vectors to understand various geometrical relationships. And you'll be able to carry out multiple consecutive vector products, I should say. This should be products. There we go. Okay, so let's begin here. And the relevant sections is the first couple of sections of chapter 14. That's 14.1 to 14.4. In 3D space, vectors are described in terms of three elements, each describing the different directions in that 3D space. We've talked about base vectors or vector bases. So in 3D space, we need 3D base vectors with which to describe our vectors. And for example, the Cartesian coordinate system again is an orthonormal basis. And that means the base vectors are orthogonal to each other. And are unit vectors. That is, they have a length of 1. So we can describe a vector on a piece of paper, for example, like we have before, v1, v2, v3, describing the magnitude of the vector in each of our three directions. Another way we've described it was with our fancy brackets, our curled brackets with v as a subscript I, and these were matrix notations. Equivalently, we could describe the same vector as a vector sum in that it is directed with a magnitude of v1 in the I hat direction, if we're using, for example, Cartesian coordinates, v2 in the j hat direction, plus v3 in the k hat direction. And so this is a sum, a vector sum of 3 unit vectors. That's another way of writing a vector. And another way that is sometimes used is v1 and v2, v3 in parentheses. So let's do a little bit of arithmetic. Starting with addition. And it's just like scalar addition. But carried out for each direction individually. In other words, v1 plus u, or sorry, vector v plus u is equal to, or we could write that as in matrix form as having the ith component being the sum of the ith component of each. Equivalently in matrix form, that's v1 plus u1, v2 plus u2, and v3 plus u3. So again, it's each component is summed individually. There are two types of vector products. And we've discussed one already when we've dealt with matrices. And the first is the scalar or dot product. And for example, the dot product or scalar product between u and v is equal to the sum from I equals 1 to 3 of the product of each component. So you take each component, take the product of it, and then sum the result of those three products. And that's also equal to the magnitude of v times the magnitude of u times cosine of the angle between the two. So visually, we could sketch this as v and u, and theta, again, is the angle between the two vectors. Or the angle separating the two vectors. And the magnitude of a vector is basically its length, which you can understand in terms of Cartesian, the Pythagorean theorem. So that's the first component of v squared plus the second component squared plus the third component squared, all taken to the square root of the sum of the squares. Some properties of vector multiplication is that it doesn't matter which order you do it. So the multiplication is commutative. It's also distributive, meaning that if you multiply the dot product with the scalar, you can do the multiplication with the scalar and one vector first and take the dot product of that with the second vector. And finally, the dot product is commutative, meaning that the sum, for example, the sum of two vectors dotted with the third is equal to the first vector dotted with the third plus the second vector dotted with the third. And I did want to emphasize that I don't remember if I stated explicitly, but the dot product of two vectors yields a scalar quantity. It's just a number. It's a scalar quantity. A couple of properties of the dot product that are notable is if U and V are parallel to each other, then the dot product is the largest possible, and it's equal to the magnitude of U times the magnitude of V, and it's because of cosine of the angle is equal to 1. For two parallel vectors, of course, the angle between the two is 0, and the cosine is equal to 1. So to maximize the dot product, you would have two vectors parallel to each other. The other situation is if U dot V is equal to 0, then theta is equal to 90 degrees, and the two vectors are orthogonal to each other. And that contrasts with the vector or cross product. The cross product produces another vector. So U cross V is equal to the magnitude of U times the magnitude of V times sine of the angle separating the two vectors, and it's directed in the E hat component, or sorry, in the E hat direction. So an E hat is perpendicular to both U and V as defined by the right-hand rule. And this image here illustrates the right-hand rule. So for example, if we have, in this case, we have two vectors A and B. So the cross product of vector A with B is equal to C. And the direction of C is such that if you aligned you take your right hand, aligned your fingers with A, and then curl them towards B, just as shown in the diagram here. And your thumb points in the direction of C. And so if, back to our example of U and V, if U is parallel to A and V is parallel to B, the cross product is a vector pointing in the E hat direction, where E hat is pointing again in the direction of your thumb. Now, a property of the vector product is if U and V are perpendicular to each other, then this gives the largest cross product possible. Right? Because U cross V will be equal to the magnitude of U times the magnitude of V, because sine of theta will be 1. If U and V are parallel to each other, then the cross product is equal to 0, right? Because again, the sine of theta, the angle between the two, will be equal to 0 in that case. So again, remember the dot product was 0 when the two vectors were perpendicular to each other or orthogonal to each other. Here the cross product is 0 when the two vectors are parallel. And going over some properties of the cross product, U cross V is anti-commutative to V cross U. In other words, the order of the product matters. And you can figure that out remembering that you point your fingers in the direction of the first vector and curl your fingers in the direction of the second. And again, your thumb is in the direction of the resulting, and therefore it matters which vector is written first. Vector products are associative, so the product of a scalar times U crossed with V is also equal to the scalar times the cross product of U and V. And they're also distributive. So the sum of two vectors, U and V, crossed with a third vector, W, is equal to U crossed with the product is equal to the cross product of the first with the third plus the cross product of the second with the third. So one interpretation of the cross product is that, well, let's see. If we take the absolute value or the magnitude of the cross product, that gives the area of the parallelogram bounded by the two vectors. Right? So for example, if we have V and U as sketched here, you can imagine they form two sides of a parallelogram, and the cross product gives the area of that parallelogram. Of course, cross products are used quite a bit, even in basic physics. And you may, for example, have seen the cross product as describing the torque. Or moment on a system. So if we describe the torque or the moment, they're the same thing, is equal to a moment arm described by vector r crossed with F. So we have a axis that's defined by the moment. We have the moment arm r, and if there's a force applied, the moment gives the component of that force perpendicular to r, and that perpendicular directed force is what would tend to rotate r, and the torque in the direction of the torque would be a vector pointing out of the page or the computer screen. And the symbol I've drawn here is a circle with a dot indicating the point of a vector, like the point of an arrow that's pointing up and out of the computer screen. So the next topic I'd like to present is the Cartesian coordinate system. And this is covered in Greenberg 14.3. And again, the Cartesian coordinate system is an orthonormal basis. With the unit vectors I, j hat, I hat, j hat, and k hat directed according to a right-hand coordinate system. Or a right-hand system. And let me bring up my diagram again of the right-hand rule here. And the unit vectors for right-hand system are oriented as I am sketching now. So this first line that I'm drawing is sort of coming diagonally but outward outward from the computer monitor, and we'll label that the I hat direction. The j hat direction is going to the right, and it's parallel. It's in the plane of the computer monitor, and k hat is also in the plane of the computer monitor. So with the right hand system, I hat crossed with j hat is equal to k hat. So you can see with the fingers in this diagram pointing in the I hat direction, when they're rotated to the j hat direction, the thumb would point in the k hat direction. J hat crossed with k hat will give the I hat unit vector. Again, these are all unit vectors, so their lengths are all 1. And that's why these orthogonal vectors give also unit vectors. Again, the sine of the angle is 1. So the resulting vector has magnitude 1. And then finally, k hat crossed with I hat is equal to j hat. And you should verify that by turning your fingers in the directions of these different axes. J hat crossed with I hat, however, is equal to minus k hat. K hat crossed with j hat is equal to minus I hat. And I hat crossed with k hat is equal to minus j hat. And you can remember these vector products using the following mnemonic sort of tool. You just write the vectors in order, I, j, and k. And if you evaluate the cross product in this direction, in this order, then the result is the next vector and it's positive. For example, I crossed with j gives k, again going in this direction to the third vector. And if you evaluate the product of two vectors in the opposite direction, the third vector is the result, but it's multiplied by minus 1. So if we were to describe a vector in this Cartesian coordinate system, say vector v, then it is the sum of a component in the I hat direction, the j hat direction, and in the k hat direction. So v would be described as v1 I hat plus v2 j hat plus v3 k hat. And again, when we do vector sums geometrically, we put the tail of one vector to the head of the previous one and then sum in that way. And in case you can't see, vector v is sort of coming out of the board and upward, sort of diagonally. So back when I first defined the vector product, for example, u times v, I described it as the sum of the products of the three components. And this is specific to the Cartesian system. If we were to use another system, we would not use this equation. And we could also write that out again as, well, we could, and well, this result arises because we could write u as u1 I hat plus u2 j hat plus u3 k hat, and we take the dot product of that with v, and we can just follow our normal rules of multiplication and multiply each component of v by each component of u, and we get u1 v1 I hat dotted with I hat plus u1 v2 I hat dotted with j hat. And you'll notice in this case we get 0 because the two vectors are orthogonal to each other. Same with the third product. And we would do all the same. We would carry out that multiplication, and the only terms that would be left are when we're dotting each of the unit vectors with itself. And of course, when we do that, we get 1 when we dot I hat with itself or j hat with itself. And we get our dot product as I first described. Okay, so this is just an illustration of how we would follow the same mathematical rules, as well as the rules that we've learned about dot products of orthogonal unit vectors, orthogonal and parallel unit vectors. Now let's look at the cross product. And that's, we take the u, which is again u1 I hat plus u2 j hat plus u3 k hat, and cross that with v1 I hat plus v2 j hat plus v3 k hat. And we carry out our multiplication like we would normally. So u1 v1 times I hat cross I hat plus u1 v2 I hat cross j hat plus u1 v3 I hat crossed with k hat. And looking at these first three terms, I hat crossed with itself is 0. I hat crossed with j hat is k hat, as you might recall from what we just discussed about our right-hand Cartesian coordinate system. I hat crossed with k hat is equal to positive j hat. Oh, I'm sorry, minus j hat. And so on. And if we continue to carry out the multiplication, the result, and collect each term multiplied by each vector, we would get u2 v3 minus u3 v2 in the I hat direction minus u1 v3 minus u3 v1 in the j hat direction plus u1 v2 minus u2 v1 in the k-hat direction. And that is equivalent to taking the determinant of the matrix formed if you put as the top row the base vectors, the bases I, j, k, and the second row the elements of the first vector of the cross product, in this case u, and in the bottom row the elements of the second vector of the cross product, which in this case is 3. So this is a very effective way of remembering how to do the cross product of two vectors, again using the Cartesian system. Cartesian right-hand coordinate system. And it's specific to that Cartesian coordinate system. Now the last topic I'd like to go over is what to do with multiple products. And in the first example, let's consider U dotted with V and then crossed with W. So the question we have to address is, what do we do first? And can we do the following? Can we do U dotted with V and then cross it with W? And the answer is no. The reason is this produces a scalar. The dot product of U and V produces a scalar. And if we try to cross a scalar with a W, then this is not defined. We can only cross a vector with another vector as defined by the cross product. So the only way we can interpret this is U dotted with V crossed with W. And since it is the only way possible, you wouldn't even need to write those parentheses. And so that is equal to the U1 times the I hat component of V crossed with W plus U2 times the J hat component of the cross product plus U3 times the K hat component of the cross product. And you know how to evaluate the cross product of V with W, again using the determinant of the matrix that I just described. So that was our first example. Now let's consider U crossed with V crossed with W. So that could either mean U crossed with V and then crossed with W, or U crossed with the cross product of V crossed with W. So there's two interpretations. So you would have to specify with parentheses which operation to carry out first. And they also give different answers. In general, they give different solutions. And for example, if we were to consider our unit vectors I crossed with the cross product of I cross J, that is equal to I crossed with K hat, and that's equal to minus J hat. Alternatively, we could cross I with itself first and then cross with J hat, and that's equal to, well, the zero vector crossed with J, and that's equal to 0. So this is an example in which carrying out the multiplication in different orders does matter for this double cross product. And I'd like to give a couple of vector identities. That is, if you take the cross product of u, or v, take the cross product of u and the vector resulting from the cross product of v crossed with w, that is equal to u dotted with w, which gives a scalar, times v. So this is a vector with a magnitude defined by the product of v times the scalar u dotted with w, minus u dotted with v, which is the scalar that amplifies the magnitude of w. So this is one vector identity. And another vector identity that comes up occasionally is the cross product of u with v and with the resulting vector cross with w is equal to minus w crossed with the cross product of u and v. Okay, so that we've covered a fair amount of territory with multiple products, dot products, cross products, and vectors described in Cartesian coordinates. So that will conclude this video as an introductory video to vector calculus.